of a conference with our keynote speaker, Elizabeth Krumbach Joseph, and she will talk today about continuous integration system for OpenStack developers. So, Elizabeth, the floor is yours.
Thank you. So my name's Elizabeth. I work at HP, currently working on the OpenStack infrastructure project. So that means I don't really work on anything at HP internally. They pull me in sometimes for small projects, but my day-to-day work is working on OpenStack itself. So our job is pretty much to make sure the developers can do their job by managing the continuous integration system and all the other stuff. You'll see lots of names on this slide here. We manage this slide deck in revision control just like everything else, and we've sort of shared the slides since we all go to conferences and talk about this stuff. And I also have to apologize because I think I've come down with a cold, so hopefully it'll all be fine, but if I forget what I'm talking about in the middle of my talk. So this is sort of the obligatory slide that you have in every single OpenStack slide deck. One thing I want to have people keep in mind is that even though I'm focusing on OpenStack in this talk, the continuous integration system we use is fully open source. You can take any of the pieces that are used by us and use them yourself. But I will be focusing on OpenStack only because it gives a really good example of how the system can be used and why we made some of the design choices we made. So while you're watching this talk, if you are interested in doing continuous integration, you might want to think about how you could do it in your own system and how you could use these tools, because they've been working pretty good for us. So how many people here are developers? And how many use a continuous integration system where you work? Okay, well, they're becoming more popular, but how about sysadmins? Okay, that's where I come from. So OpenStack itself is, if you think of something like Amazon EC2, that is run by Amazon's proprietary software that runs their cloud. Part of it is based on Zen, but otherwise we don't really know a whole lot about it. OpenStack is sort of the open source answer to this platform. So companies who want to run their own clouds, like Amazon runs a cloud, they can use OpenStack to do that. It also can be used as a private cloud. You can call on to OpenStack to run a hybrid cloud. So you can run part of your application in a public cloud, say hosted by HP or Rackspace, and then you can run part of your cloud on an internal cloud that you're running OpenStack yourself. And the really cool thing about that is you don't need to modify your environment very much. You're still using all the OpenStack calls and all the OpenStack features that you'd use on your private cloud or your public cloud. So OpenStack itself is made out of different pieces. So there's a compute project, a networking project, several storage projects, and then other things. We're working on orchestration, metering, so people can actually bill people and use a project that's part of OpenStack. So it's all these different projects that have sort of different leadership and different developers, and they come together to build what is OpenStack, which has influenced a lot of our design decisions, which I'll talk about. We also have programs. These are sort of efforts that are aligned with the OpenStack project itself, but not necessarily core components of OpenStack. So you'll have things like documentation, translations, the OpenStack infrastructure team, which I'm part of, is one of these programs. And all of these sort of have to be part of the OpenStack project, and because they're essential to having a full project. In the infrastructure team, we manage the continuous integration system and then all of the developer resources that a developer may need throughout the project. We release every 6 months, which may be a familiar release cycle to a lot of people. I think Ubuntu does a 6-month release cycle, and I think Fedora still is on a 6-month release cycle. When OpenStack was started, it was a lot of Ubuntu people working on it, and they really liked the 6-month release cycle, development-wise. So when they started working on OpenStack, it felt very natural. We also have a design summit every 6 months, which is co-located with a user summit. So we end up getting a really, really big conference together. I think the last one had something like 4,000 people at it. So we'll have a user track, which has a lot of users coming in to watch sessions and learn about upcoming technologies in OpenStack and sharing their stories. And then we have 4 days of development tracks where we all get together and sit in a room and work on what we're going to accomplish in the next 6 months. In this release cycle, we have everything committed directly to the trunk, so the master branch. So we have to do a lot of testing to make sure that master branch doesn't break. And then we have milestones throughout the project. So we have a freeze, and a feature freeze, and release candidates, and all these things, so that people have stopping points within the release schedule. Contributions to OpenStack come from a variety of places. I work for a for-profit company, and a lot of the people who contribute as well do. But there's also a lot of people who don't have an affiliation. They might be volunteers, maybe they just didn't sign up for an affiliation. We're gonna take off. There's also nonprofits who are working on this, government organizations, universities, scientific endeavors who are working on this. I know CERN uses OpenStack pretty heavily, and they contribute a fair amount. We had someone from the NSA actually come in and talk to us about how they use OpenStack. They couldn't tell us much, and it's kind of scary that we're enabling them to do that big data processing that George was talking about yesterday. But it's being used in production in a lot of places. DreamHost, we recently learned, has a massive OpenStack deployment that manages the object store for a lot of their applications. So it's not really a public cloud, but people are accessing it through their interfaces seamlessly. They don't even know they're using OpenStack. So as part of this, we needed a system where all contributors could come in and work in the same space. One company is not dependent on another company to make contributions. And as such, we have to varied degrees of quality in the contributions, and then during certain parts of the cycle, we have more contributions than others. Like around feature freeze, we have a lot of people coming in to get their features in right before they get the cutoff. So one of the things we needed to do is have consistent tooling across the entire project. I quickly mentioned that the compute module and the networking module and the storage modules, these are all sort of run as their own projects. So they each have a project technical lead. They each have their own core developers. And when they go to the OpenStack summits, they largely work in their own teams and have their own blueprints. And then we sort of come together to make sure everyone's on the same page. But they largely run as separate projects that come together as this thing called OpenStack. So what we wanted to do in this development workflow is make sure that everyone has the same tools, so that if you're working on the compute module and you realize that there's a bug in the networking module, you can go over to that, submit your change, and then go back to your work without having to learn anything new, without having to figure out what development tools are being used by that team, because they're all pretty much the same. The infrastructure that we run has a lot of stuff in it. I'm not going to read this slide because it's a lot of stuff. I'll talk about Garrett, the code review system in VCS, and the test build automation. But everything else on here is also part of what we work on. So if a project needs a mailing list, we're the ones who work to set that up. Etherpad, paste bins. We run a bunch of IRC bots because the project is mostly collaborated on in IRC. And we use Launchpad, the one hosted by Canonical, to do bug tracking and blueprint tracking, and right now we use it for our single sign-on. We're slowly moving away from that as we're developing a new bug tracker because the world needed a new bug tracker. That's where we are now. We also do all of the systems administration for all of those systems is in Git. So we have git.openstack.org, which we also run, and that's where we publish all of our configurations. So system configuration, Puppet configuration, pretty much all the details you would need to run the infrastructure is in our public code repository. Anyone can see our changes. If you go to review.openstack.org and search for OpenStack Infra, you can see all the changes that are related to the infrastructure. By default, it just brings up the page that has the latest fixes and changes in OpenStack itself. So you'll see infrastructure changes and OpenStack changes, compute, networking, all kinds of changes. Anyone can see the review.openstack page. Anyone can sign up for a code review account, which has been really helpful to me because I sometimes pull in friends who aren't working on OpenStack, but maybe they're a CSS expert, and I'm working on fixing some CSS somewhere, and I'm really bad at web development. So I ask them to come and look at a change, and I can just upload it, and they can look at it, and they can sign up for a code review account. They can leave some comments, and they don't need to make an investment in OpenStack. It's just signing up for an account. And also anyone can write and propose changes both to the systems administration side that we work on and OpenStack itself. If you're working on OpenStack, your development pretty much looks like using Python, using DevStack, which is the development version of OpenStack. So when you have a new patch, you'll apply it to the DevStack that you downloaded, and then you'll test your patch on that. And then we use DevStack as well in the actual testing in our continuous integration system. Every time you upload a change, that automatically triggers a run of a bunch of jobs that test your change, and then it reports back to the code review system saying that's done. And then before any code is merged, we also have it go through all of the tests again to make sure it's all working. People collaborate on Freenode. We have a few channels. We have actually several meeting channels now, development channel, and then a lot of projects have their own channels as well. It's because we work at all different companies all around the world, so time zones are a problem. So we don't really do conference calls very often. Some teams will do a mid-cycle meetup. So in addition to the OpenStack Design Summit, they'll find a time between releases where they'll all get together in one spot. So I'm going to Frankfurt next month for my team sprint, so that should be fun. Right, so we call this running tests before things merged, project gating. A lot of organizations, either they don't do testing on their software at all, which is pretty much how a lot of open source has gone in the past. Sometimes it's companies who are doing testing, but typically this testing is after the code has been put into the repository. So there's a development repository, and then code is tested once it's hit the repository. For us, we don't let code merge at all until it gets to it passes all of our tests. This means that one company can't break OpenStack for everyone else, which is very nice because if one company broke something and then all of your engineers that you're spending time on can't get their work done, that's a very bad spot to be in. So we try to make sure that DevStack, the development version of our software, is always working. So we hope that this means that bad code doesn't land, since it has to pass our tests. And it makes it so that the process is the same for everyone. No one company has a lot of developers who have, commit access to our master branch. Everyone has to pass the tests. Everyone has to go through this full code review system. And of course, everything is automated. This is a screenshot from status.openstack.org/Zuul, Z-U-U-L. And it shows some of our queues that we have. So we've got a check queue over here. These are tests being run that are being checked. So someone uploaded code and the tests are running against it. So you'll see the little dots here. So the green dot means that it's passing, the red one means it's failing, and it will continue going through its tests until it completes, even if it fails, so that the developer has a full report that comes back to them about what it's failing on. In the middle here, we have the gate queue. That one is the one that the queue that happens right before the code merges. So humans have reviewed their code, and now it's gone into the gate, and then it gets merged. You'll see there's a little red dot down there that's sort of off the little subway map. That means a change is failing, and so we're going to continue those changes, but then this change here won't be depending on that one anymore. And I'll show you a cute little animation in a bit on how that works. And then off to the other side, we've got a post queue, and we have several other queues in here. These are just the ones that I grabbed in the screenshot. And these are typically things like you would build, we build a tarball of each commit. We build the developer documentation for each one, which uses Sphinx. So the post queue will build all that documentation, and then we have a release queue that actually will publish documentation or publish the tarball to our Apache servers. And this is, I'll be referring back to this a few times, this is sort of the overview of the entire continuous integration workflow that we use. So you've got a little computer down here. This is a person's computer where they're running Git and they're working on their changes. Oh, sure. Thanks. So we've got the local changes. You submit them up to Garrett. And I'll talk about all these pieces more in depth, but just so you get an idea in your head of how this all works. So you go to Garrett, and then it heads off to Zool, which I showed you that screenshot of with the little dots. Zool is sort of our gatekeeper system that manages how the commits are coming in, making sure everything is tested against each other. That gets sent off to Gearman, which is sort of a job queuing system, and then it's sent off to our Jenkins servers, which actually do the tests and farm that out to the nodes on our network that can run the tests. Once Jenkins says it's okay, it comes back to Garrett and says, this looks good or this looks bad, you need to fix something. And then in Garrett, people will leave comments and do code review and other things. And then once a couple of humans have approved the code, it'll go through the whole system again, Zool and Gearman and Jenkins and everything, come back to Garrett, and then it will finally be merged into the code repository. So this is what I see in my work, but if you were a developer, this is what you would see. This is a much prettier graphic because I made the other one and I didn't make this one. So people are checking out the code, so they're doing a clone to their local environment, which is this box over here. So say they're working on Nova, that's the compute module. So they do a clone of that, they branch their code to work on whatever they're working on, run git commit to commit the code, and then instead of doing something like a pull request, we have this tool called git review, and git review has all the special magic you need to send things up to the Garrett code review server. And this little box here is pretty much that big picture I showed you before. But the developer doesn't know that there's Gearman and Jenkins and all this other magic. They just know that when they upload their code, the robots come back and tell them whether it passed or not. And then up here, the automated testing, again, that's right before it hits the code repository, and then after it's been approved, so it gets tested again, and then it hits the master branch when everything passes. And so the next person to clone it will get your patch. So Garrett, I keep talking about Garrett. I'll show you a screenshot in a moment. It's a code review system. It's used for Android, developed by Google, and they use a version of it internally as well. Unfortunately, it's written in Java, which I don't know, so Garrett is a mystery to me. But it's a patch review system based on Git as the revision control system. It has hooks that you can listen for. It supports JSON queries, and it has an event stream, which is pretty much the most important part about it for us. Zool will watch the event stream, and the event stream has things like someone uploaded code, someone put a +1 or a +2 or an approved, and then Zool will then do what it needs to do based on that. It has a couple of categories by default. So it has a verified category, which we use for the robots. So when the code passes the tests, Jenkins will put a little check mark in the verified column. And then code review is for people, so people can do things. We also upgraded recently to version 2.8, which has a REST API, which is pretty nice, and people have been asking about it forever. This is what Garrett looks like. So you'll see at the top, it sort of prettyifies the commit message that you normally send to Git. So you'll have a user, the owner up at the top. It'll tell you what project it is, the branch that they're working on. Topic is actually their local branch. This is actually a screenshot from a merged change. And then over there, they'll have a commit message that's nicely formatted. The change ID in there, that's used, I mean, that's the Git thing, but it's also used by Garrett to keep track of what changes are being uploaded to it. And then I mentioned all of these columns here. So we've got the code review column that's for people, the verified comment column that's for robots. And then you've got all these things. So you've got this, in this example, a bunch of third-party testing has been submitting changes. So IBM has a Power KVM testing. VMware has this thing called Minesweeper that they run against the code. Microsoft has Hyper-V continuous integration hooked into our system, so they report results. We have something called Turbo Hipster, and then Zen has a continuous integration system, because we run everything with KVM. So anyone who wants to do extra testing, they can hook into our system and report results. And then once they've been a good citizen for a while, we'll give them actual voting rights on this. So on here, you'll see the IBM and VMware and Hyper-V. They don't have anything in these columns yet because they're not voting. But let's see, Zen server votes, Turbo Hipster votes, and then you've got all these people here who are giving code reviews. And if you scroll down here, let's see. So you see here, I'll open up this file in a moment. It shows a diff of the two files that are being changed. And then you get all the replies. So here's from Turbo Hipster giving back results. IBM Power KVM. In this screenshot, it's failing, and that's one of the reasons they're not voting yet, because maybe their system isn't working right, or we're testing the wrong things, or they need to fix things up before it actually becomes voting. Jenkins is our system, so these are things that it has to pass. You'll see this one down here that's a failure, but that's okay because it's not voting. Typically, these are put in when someone's working on another test that they want to add, but they don't want it to actually impact the result yet, so it won't give a -1 if this one fails, because maybe this one's not stable yet, or again, they need to fix something. And then as you continue going through here, you'll see people leaving comments. And then finally, it'll go through that gate queue. And then it's all success, hooray. And then it's finally been merged into the repository. So this is pretty much where developers live in OpenStack. They are working on Garrett all the time, the code review system, doing code reviews, making sure that their code is being reviewed by other users. And this is what it looks like on the little diff. So in this case, it was a very simple change. But you can see them side by side. You can expand it if you want to look at the entire file. And again, this is a very small change. Some of the changes are pretty big, but we try to keep them under 400 lines because then it gets too overwhelming to review. I mentioned we're using Launchpad right now. One of the nice things, again, about using Garrett that's so scriptable and nice is we can put a bug in the commit message, and then we write a hook that grabs the bug name and then automatically works with Launchpad's API to report back to the bug tracker. So you can, when you have a change, you can put the commit message in with the bug number. It'll leave a comment in Launchpad saying, hey, this code is up for review, so anyone looking at the bug will know that there's code that's available for review. And then when the code actually merges, it will go in and leave another comment saying this is the bug, this is the code review that fixed it, and then it will automatically close the bug, so you don't have to work on additional things to do when you close a bug. You upload your code, you link it in the commit message, and then it all does everything itself. If you go to review.openstack.org, this is sort of the screen that you will see. It automatically defaults to everything that's open. Beyond that, you can search for specific things. You can search for things that have been merged already. You can search for specific projects, specific sub-projects. And as you can see from the side over there, people are making changes to this code review system every few minutes. On busy days, you'll see like the timestamp may be like every single minute someone's making a change to our code review system. So it's it's used a lot. So I briefly mentioned Git review. That's the tool we use to upload changes to the Gerrit server. So as you can see, you just do a git commit as you normally would, write your commit message. And then instead of doing a pull request, you type instead git review, and that will automatically send it up to Gerrit using your SSH key. And then you don't need to worry about any of the strings that you might have need to use in Gerrit, because Gerrit's actually kind of complicated to contribute to, or to upload things to. So we have this tool that does it all for you. You can add configuration to Git review, but by default, any developer can come along and just use it without any configuration. And people have started using Git review outside of OpenStack as well, which is exciting for us because we want these tools to be used by other people. So a little bit about the types of testing we're doing with our continuous integration system. We start off by doing unit tests, which are pretty easy. A developer probably should be running unit tests before they upload their code, but they don't, so we make sure that they are run. And then beyond that, we have the integration tests, which again is very important for OpenStack since we have a huge project that's made up of lots of different little projects. So you want to make sure that your change to the compute module will not impact networking. And if it does, you want to be notified notified about that. So we run all of our tests on virtual servers that run on HP and Rackspace clouds that are donated to the project. And then we report the results back to the developer in Gerrit. So if their test fails, you won't see a little success next to that. You'll see a failure and then a link to the logs. So then the developer can go and look at the logs and find out what failed. We have some challenges still with this system. One of them is the fact that we're only using virtualized servers, so we're not testing any sort of hardware configuration in our default tests right now. We're not doing anything except for virtualized testing. We do have a OOO project, which is OpenStack on OpenStack, and they've started doing some actual bare metal testing. But again, the hardware specifications on that are very simple, and the servers being used are ones that are known to work with OpenStack. So there's not really anything that we're doing that's testing the hardware, really. We're just testing how it's being used on a specific set of bare metal. We have this script, Gerrit git prep, and that's actually the script that goes and pulls out your code from Gerrit and then applies it to our DevStack instance, which I'll talk about in a moment. So it'll grab the branch that you want to test, clean up the tree to make sure it's all good and fresh and new, and then it'll merge your change into the DevStack instance, and then it'll run all the tests. So this becomes important a bit later when we actually call it. The way we found early on that we needed a way to manage this fleet of servers that we use for testing. So once a day, we create an Ubuntu image that we're going to use for testing, and we'll boot that fresh image every day and apply it to a bunch of servers that we have. And then every time that we need a new VM, we'll just flash it with that image throughout the day. And then we'll have DevStack running on that, and that's where we'll run all of our tests. We had a few problems with this when we first implemented it. One is that tests can be really slow. We were not parallelizing anything. It was all serial testing. So we were waiting on everything to be done in sequence. We also learned really quickly that the cloud API calls can sometimes fail. So sometimes when you call for a VM to be loaded up, it doesn't come up. This happens on pretty much all the clouds. It happens on Amazon and HP and Rackspace and everyone's cloud. Sometimes when you call a VM, it doesn't come. So we had to deal with that failure case so that we're not calling a VM and expecting it to actually be there. We also learned really, really fast that external services are unreliable, especially when you're developing at the velocity we are. we found that if we were cloning from GitHub for a while, and if GitHub is down for 1 second, like 4 of our changes will fail, because it's like we're doing so much stuff. So we can't rely on things like GitHub. We can't rely on the external Python mirrors. We have to pretty much build all of that stuff into our own. The only thing that sometimes code will call, like they'll do a wget against a file that exists somewhere on the internet. And so there's some things that we can't really control. We also use the Ubuntu package repositories that come with our cloud providers. So sometimes those can fail, but right now we haven't really found a need to replace those yet. So we found that these are some of the problems that still exist, but we've been able to work around largely. So I sort of talked about this, but pretty much what we're doing each time to work through these things. Every test has a brand new node that's used. We never reuse a node for a test, partially because anyone can upload code to our system, which means that we're running untrusted code on our VMs, which is one of the reasons we don't do a lot of bare metal work, because VMs you can throw away. Bare metal has the potential to actually have people upload malicious code and destroy the machine. So we prefetch everything in these images that we build. So all the code repositories we need, all of the Git repositories in OpenStack we might need for a test, we cache all of those on the image that we build. We create a snapshot of that, and then we load it onto the pool of nodes that we maintain. And then we started parallelizing our tests. So they're no longer run in serial. We're using something in Python called test-r rather than nose to do the tests, so we can sort of determine what depends on what, and then what can actually be run all at the same time. Zool is that thing I showed you a picture of, and we'll have a demo in a moment. That's the one that is between the code review system and Jenkins, which actually does the tests. So that manages the flow of tests and everything. And then make sure that everything is tested against each other and can do a bunch of stuff at the same time. Again, most of our bottlenecks have to do with running tests and making sure they've run in a parallelized mode. We also assume that things are going to succeed. So when we have a list of changes that are in the queue, we'll build everything on top of the change that's in front of it. And then when that change fails, I'll show you in a moment, we kick that out and then start the tests over. So this is a fun little simulation. So right down at the bottom here, you've got the Nova branch and the Keystone branch. These are 2 pieces of OpenStack. So let's say we've got some changes. So we've got a Nova change, a Keystone change, and another Nova change. These are ones in the queue. They're in the gate, perhaps, and someone wants to merge all of these changes. So the changes will start going. All the tests will start running. And we'll see some of these start turning green. The first 2 have started turning green. That means the tests are succeeding and things are good. In this example, Keystone had a problem. So everything behind it in the queue, which means that other Nova change, is starting to fail. So what we do in this instance is we kick Keystone, we disassociate that 4th change from Keystone because we think that change may be failing because it's depending on the Keystone change. We then kick Keystone out. We allow the tests to finish so that developers can see what all is failing in that, but we don't have it in the dependency queue anymore. And then we reassociate this 4th change with the 2 patches in front of it, and then allow it to start running all of its tests. So it's no longer depending on the failing test, and in this case, it's actually starting to work. So now this one turns very green. That means all the tests have gone, and it can now merge into the code repository. Hooray. Same goes for this one. Everything's passed. It's all good. Code goes into the code repository. Keystone over here has finally finished all of its tests, and it's failed. So we just kick that back, and so Jenkins will then report back to Garrett with all the logs and everything the developer needs to see in order to fix whatever's gone wrong. Maybe someone has changed the code out from under them and they need to rebase, or something else has happened that caused their code not to work. And then this guy, he's turning green too, because finally he's not stuck behind that keystone change, and that one can merge into the repository as well. So that's Zool. Zool is highly configurable. It's got YAML-based files that you can edit to add different sorts of things to its queue and have it do different behavior based on what's happening inside of Garrett and what reports back. We also configure what we run on the projects inside of Zool rather than doing it directly inside of Jenkins. We use a tool called Jenkins Job Builder, which a lot of projects outside of OpenStack are now using. It has YAML-based files, as you can see, that define what project is being tested and then what tests are run in each queue. So you've got that check queue and the gate queue and the post queue. So in this example, it's a very simplified example of what we run in Nova. If you look at our actual config file in our Git repository, the Nova tests are much huger than this. But for example, this is running several Python tests, and then it runs the devstack VM test. In the gate, it runs the same things as it does in the check queue, where that happens right after someone uploads a change. In the post queue, in this one, we're building the tarballs, we're building the documentation, we're building we're preparing the translations for being uploaded to the translation system. And then in release, we're actually moving the tarball over to the Apache server that's going to serve it, and then we're moving the documentation over to the documentation server. We also have jobs that are templated because we're going to run for instance, we're going to run the Python tests on every single project inside of OpenStack because OpenStack's written in Python. So we don't really want to write that multiple times, so we have templated jobs inside of this project. And so, yeah, here's the example. So in this case, this is the template for PEP8. So whenever we want to do a PEP8 check, we can just include the job template into a file, which you'd see here. So under jobs, you'll see Python jobs, and then you'll see PEP8 jobs, and name expands into the name of what's above. We also have a lot of logs. Every successful, or every run through our continuous integration system that completes creates about 300 megs of logs compressed, which means we've got terabytes of logs, and we used to keep them forever, and then we kept running out of space, and we said this is impossible, well, also the size of them has grown over time, because we do more tests these days, and we have more projects. But then we started keeping them for 6 months. I wrote this massive find line that goes through and finds all of the logs and does a rotation, because log rotate actually couldn't do it, because it would take days. Log rotate turns out is not really built for rotating massive logs, but find does great. So we have all these static logs that sit on one of our servers. We also filter a bunch of logs through Logstash. These are selected logs that we filter through because, again, terabytes of data, putting it all into Logstash is impossible. So we select specific logs from each project, put them into Logstash, and keep 2 weeks. Because once they're in Logstash, they're heavily indexed, and then we're talking about lots and lots of more terabytes of data. And then from there, you can search. We have logstash.openstack.org, which is the Kibana interface for Logstash. And in that interface, you can search for failure strings or anything that ends up in the logs. This has been really interesting for us. We have this elastic recheck project where people will identify strings that happen in failures a lot. Either it's an infrastructure failure, like a VM randomly goes down in the middle of the test, which totally happens. And there may be something in the logs that indicates that the machine is all of a sudden shutting down. So someone can find that string that they find in the logs. They can put it into Kibana or the Elasticsearch API, and they can see how often this happens. So we took that one step further and decided that, when someone finds one of these bugs, a bug with our infrastructure, or one of these bugs that only shows up 5% of the time because maybe you have a race condition in one of the projects or something similar, people can actually find the place where that error happens and then create a bug report and then add it to our project called Elastic Recheck, which will then run against every single code contribution that comes in. So if this error if someone has submitted the bug report, a applied it to our elastic recheck repo. When someone else runs into the bug, they'll automatically be notified in Garrett from our elastic recheck service about the fact that their patch has hit this known bug in the infrastructure or that it's a race condition or something similar. So we're able to now drive automatic failure classification through this log stash stuff. Again, it only goes back a couple of weeks, but that's usually enough for us. And this over here is our complicated log stash setup with Kibana and Elasticsearch and all that. It took actually a few months to put this infrastructure together because it was complicated and we had so much data floating around. So in the Garrett screenshot I showed you, there were tests from Hyper-V and VMware and all these other companies who are doing third-party testing. We also do this for hardware companies. So a lot of hardware companies, especially in the networking space, want to make sure that their hardware is working well with OpenStack. So we allow them to, again, just like the virtualization companies, the hardware companies will have little robots that run their own Jenkins server. They listen to our Garrett event stream so they know when a change is uploaded, so then they can run it on their own continuous integration system. And then they report back to our system. So in Garrett, you will see comments from all these third-party systems, and also, voting if they're mature enough for that. The great thing about this is we need to set up their account early on so they can listen to the Garrett event stream and so that they're in the right category to be one of our reporting robots. But beyond that, we don't have to worry about it. So all this hardware gets tested by the vendors who actually want it to be tested, and we don't have to do anything. Developers can use this knowledge or the feedback from the companies and see maybe something has failed on their patch, but maybe they don't care about that company's network driver. So maybe they'll want to approve it even though it failed on someone's driver. But the company is then notified that their patch that this patch failed, and so they may put engineer effort on fixing it. Or they might not. Or people may not want their change to break anything, so they'll wait till all the third-party stuff has come back. But this has been really helpful to us because we've gotten a lot of requests to expand our testing infrastructure, but we have limited resources and a really small team. So. We also have multi-mastered Jenkins, which really isn't a thing. If you talk to Jenkins people, this is not a thing. But we're able to do it because we don't send our tests directly to Jenkins. We use this tool called Gearman, which interfaces between Zool and Jenkins to actually farm out the jobs. So Gearman will find one Jenkins server that it wants to use, and the Jenkins servers don't actually know about each other at all. And then in this infrastructure, we've got something, this says 600 plus, but we're actually over 800 test nodes at this point. And one Jenkins server can't handle that as much as you want to throw RAM and CPU at it. It runs Java, so. And this is just a pretty graph of our test nodes. Again, this slide's a little dated. It's maxing out at 600, but we're actually maxing out at over 800 nodes now, which means that HP and Rackspace are donating lots and lots of nodes to us, which is very nice. These are managed by a tool called NodePool. NodePool will identify when a test has completed, or it'll see when a test comes in. The test will be running on the server. It takes about 45 minutes to run a full OpenStack test. Once the test is complete and the logs have been uploaded to our log server, NodePool will be notified of that, and it will destroy the VM, because again, we're not reusing them. And then it'll grab the image that we created, that once daily image, and flash a new server and prepare that so it's ready for the next test to come. So this is a fleet of servers, 800 servers that are across 2 OpenStack clouds. So we're doing sort of hybrid cloud ourselves. And that's Rackspace and HP. And then in addition, our O program also references 2 private clouds, one run by Red Hat and another one run by HP that actually does bare metal testing. So we have 4 clouds that NodePool is regularly talking to, all OpenStack and all configured differently, but we're able to talk to it the same way, all these different clouds, because it's all OpenStack, and it's just Nova commands and Neutron networking commands, and they're the same across the different clouds. And this is a picture of some of our graphs of how NodePool is doing. Where's the key here? there we go. So it shows in the yellow, that's how many are building at any given time. The green is how many are available. So when a change comes in, it's got some nodes available. The blue is the ones that are in use, so those are currently running tests. And then the purple is the ones that are being deleted. OpenStack has a queuing system, so when you put something in to be deleted, it sort of sits in the queue until it's time for it to be deleted, so it may take a few minutes. That's why we've got so much purple. And then it all comes back down to the orange, because once it's deleted, it can come back as another server. And that is our continuous integration system. And it's a lot. So, questions? Everybody's afraid.
Any questions?
I'll put this up here, so if you want to look.
So you use OpenStack to test OpenStack, right?
I do, but it's a known solid version of OpenStack that HP and Rackspace run.
And that's a good thing, you know.
Yeah.
When you're doing compilers, then when you host yourself, that's a great milestone.
Yeah.
So did you think about optimizing any of these things in terms of your just power use or something, or just not that big? Don't feel that important?
So we're always optimizing different parts of the infrastructure. So it really becomes, when something becomes a pain point, usually is when we get around to doing it. So.
Thanks.
Yeah. There's a question in the back.
So could you tell us a little more about how Git review works? Because I'm in an environment where we use pull requests, and that has the idea of somebody, in our case, the developer, if they've made their own changes, submits a pull request and won't commit it themselves until they've had approval from other people. But I can imagine a time when sometimes those pull requests are owned by a code owner. So do you have something like that going on in this Git? How does Git review manage who owns which bit of code?
So it's actually mostly handled through Gerrit. So Git review will allow you to submit code if you have an SSH key that's in our system and everything. And then when someone else wants to submit something, they can actually co-own your patch. So they download it from Gerrit using review.openstack.org / your commit message, whatever. That's our Gerrit Git server. So then they actually download it from Gerrit. And then when they use Git review, they'll actually use, when they commit their message, they'll do commit-a -amend, which will grab the change ID from Git. And when you use Git review to upload your change, Gerrit will see that it's the same one in your commit message, and it'll associate it with that patch. So you can steal other people's patches, and some people are more okay with that than others. Partially because it messes up with stats a little bit, and maybe you don't get credit for that if you're the one who's not the original patch creator. But yeah, it's not really Git review it does it, it's Gerrit.
Any more questions? Don't be shy. Use your time now. I have a question.
Oh, sure.
You have mentioned a lot of logs, and can you say a bit more about that? Logstash and the find thing you mentioned?
Yeah, so let me bring up that slide. You see, that's a stack of pancakes. So this is sort of how it works here. So the logs are generated by the VM that Jenkins uses. So these are system logs, service logs, pretty much every single log that is generated. Some teams turn on debug in their logs, which makes them crazy massive, and we don't want them to do that. But sometimes it's just warning or error logs. So that's why we have so many logs for each test run. It's because we want to know when something goes wrong. We want the most detailed possible logs. And then it goes into this whole big mess here. So you've got the Jenkins masters and the slaves, and they talk to each other through SSH. The Jenkins master then gets the logs from the slaves and sends them to our log archive. and also has 0MQ running, which will send them to another Gearman worker, which is unrelated to the one that's in our continuous integration system. But the Gearman worker and the Gearman server then go down and send things to the log stash stuff. So it's got this actual big queuing system built in. So sometimes our log stash is actually a few hours behind the actual rest of the infrastructure, just because it takes so long for things to get processed and indexed inside of log stash. And actually, if you go to, we have a listing of all of our servers at git.openstack.org under the infrastructure. And we've got something like 12 Elasticsearch nodes and 8 Logstash nodes. We've got a lot of servers running all of this stuff to process the logs in time. So,
Okay, thanks. And do you really have to clean the log stash, as you mentioned, or
I'm sorry.
do you have to clean the log stash when it actually gets bloated with a lot of stuff?
So all we do is, there's actually a feature in Logstash where you can only keep a certain number of logs, so it cleans itself. So after 2 weeks, the logs are expunged from Logstash, and then more logs can come in. And then we've also tweaked Logstash some, so it does more limited indexing, because when we first implemented this, it was something like, for 1 day of logs in OpenStack, which was about, I don't know, say 200 gigs, we were taking up 2 terabytes of data in Logstash because of all the indexing. So we've had to pare that down a bit because it gets pretty insane very quickly. We don't have, it's the cloud, right? So you've got unlimited storage space, but not really. It's too much processing, especially when some of it's not necessary.
Can I ask an OpenStack question, not related to CI?
Sure.
So for small projects or for independent developers who just want to play with different parts of OpenStack stack, what are our choices? Maybe I have some small applications that actually want to run in production, maybe on OpenStack, but that's not necessarily what I would do in the first as a first step. Maybe just have some OpenShift, for example, is cool, but it's something that sits above OpenStack, so I can't get myself, I can't experiment easily with the OpenStack components.
So there are a few ways you can go about this. The way that I tend to recommend people go is just grabbing DevStack. Even though it's the development version of OpenStack, and that's scary, we've tested it, and we use DevStack to do all our tests. So at any given time, DevStack should work. So that's the easiest way to do it, and plus, with DevStack, you get to sort of try all the components that are in development now. So maybe by the time you're ready to actually deploy it in production, those development version stuff will actually have hit the stable version. So you're getting used to what's upcoming. If you don't want to use DevStack, so DevStack's really easy. Like, you download a shell script and then you run the shell script. Don't do it on a machine that you care about, because it messes up your repositories and does horrible things to Python, and DevStack destroys your machine. So I'd recommend doing it on a machine that you're dedicating to playing with OpenStack.
That has to be a physical machine, or can it be a...
No, it can be a VM.
Okay.
Yeah. It just needs a fair amount of RAM, because it's a big thing. So DevStack is one way to go. If you don't want to go that way, there's a set of Puppet modules that are available. I think Chef creates modules as well that will allow you to deploy an OpenStack from the stable version. And then also you could just go through the install directions, which are kind of difficult because they stop at a lot of points and say, and now you have to choose your virtualization technology, and now you need to choose your queuing system, now you need to choose your database. And as someone who's coming to OpenStack pretty new, you'll have no idea how to do any of that. You'll have no idea what queuing system is better or what database. You just want things to go. So if you go that route, I'd recommend looking at what DevStack uses. DevStack, again, is just a giant shell script. So you can actually look at what MySQL, what SQL database DevStack uses, what virtualization technology it uses, and then plug that in when you're installing OpenStack yourself. So there are a few ways, but I'd go with DevStack just because that's the easiest one.
Any more questions? No? Okay, then we're done. Thank you very much, Elizabeth.
Thank you.